So in the last day, I have discussed the Drude model regarding the free electrons in crystals and free electron gas in metals. So today we are going to discuss about the ground state properties of the electron gas, which is the consequence of the Sommerfeld theory of the metals. So as the last class concludes that according to Drude and Lorentz, the conduction electron are treated as the free particles as if they're electron gas molecules which obey the classical laws of mechanics and statistical mechanics. Furthermore, from classical statistical mechanics from the kinetic theory of gases, the average energy of a free electron is 3 by 2 kT, which comes from the equipartition energy. And if we consider the gas in three-dimensional, then 3 times half kT, that is 3 by 2 kT. Thus, if a metal contains n, capital N free electrons per mole, then the average energy of the electrons per mole should be energy average is equals to 3 by 2 capital N kT, which is 3 by 2 RT, where capital N is the Avogadro's number and R is the universal gas constant, which is N times K. Therefore, a easy consequence of this is the electronic specific heat, which is given by C, if this is specified by C, which is del E del T, that is 3 by 2 R, or simply it is 3 calorie per mole degree Kelvin. But interestingly, this kind of electronic contribution of the specific heat, and in case of, I would say, the heat capacity or the magnetic susceptibility in a solids cannot be described by the classical statistical mechanics, where we shall consider the electron gas as the uh, uh, free free molecules, as in case of the ideal gas. And the difficulties which is encountered in the classical free electron theory in attempting to explain the observations, right, of the heat capacity and magnetic susceptibility of free simple metals are corrected in a simple and satisfying way on taking account of the requirements of the Pauli exclusion principle, right? As electrons are fermions, and we are familiar with the central and the crucial part played by the Pauli exclusion principle is that in accounting for the composition and even the existence of the periodic table of elements. The most elementary statement of the Pauli exclusion principle, as applied to isolated atoms, is that no two electrons, right, no two electrons of the same atom may have all their individual quantum numbers equal. So the individual quantum numbers in an atom may be taken as the small n, which we call the principal quantum number, the small l, which is called the orbital quantum number, small m suffix l, which is the azimuthal quantum number representing the projection of l on a given direction, and finally ms, which is the spin quantum number, and which may be either plus half for the up spin and the minus half for the down spin. There are two orientations of the spin. As we know, spin is a quantum number, comes from the uh, quantization rule, and there are two possible spin orientations are possible, and that's why up spin or down spin, there are two spin components for electrons. So as we start from the elementary elements in the periodic table, that is hydrogen atom, where it consists of one electron only, then my principal quantum number becomes 1. The orbital quantum number as well as the azimuthal quantum numbers are 0. And spin, if is spin regarded as the up spin, then ms is half. And then the next electron added in forming in the ground state of the helium, as helium is the second element in the periodic table, then the n becomes 1, L equals to 0, ml equals to 0, and ms equals to minus half. Means the ground state of helium, which has two electrons, must occupy the set of quantum numbers this, where in helium all the sets of quantum numbers associated with n equals to 1 are fulfilled or occupied. So that when I go to the lithium atom, the third electron in the ground state must start from n equals to 2, and we can complete the set by taking L equals to 0, Ml equals to 0, and Ms equals to plus half. So it is evident when we try to determine the consequences of the Pauli principle for the conduction electrons of a metal that we must first set up a proper system of quantum numbers for the problem, a system which will specify the state of the conduction electrons in the same way as the set of quantum numbers n, l, ml, and ms, which specifies the state of the electrons in the problem of the free atom. So we quickly move on. For this present purpose, what we are discussing is the quantum theory of free particles in a box. The most important fact about the free electron is that there is a wave associated with it of wavelength lambda equals to h upon p, where h is the Planck's constant, p is the momentum mv of the electron considered to be free space. So this is the de Broglie relation. As we all know, the wave numbers of the electron has been demonstrated by the many experiments. In the first instance, the electron diffraction experiments done by Davison and Jarmar, and obviously G.P. Thomson. So in these experiments, one detects the beam of electrons diffracted on reflection from the surface of a crystal or diffracted in passing through a polycrystalline foil. The angles at which the diffracted electron beams are found are just the angles satisfying the Bragg condition, that is 2d sine theta equals to n lambda, where the wavelength in the Bragg condition is to be calculated from the de Broglie relation above, and the electron momentum p is related to the accelerating voltage applied to the electron beam by p is equals to 2me to the power half, as e is equals to half mv square. So where E is the energy of the electrons, and a convenient practical relation for the electrons are lambda in Armstrong turns out to be 100 over V to the power half, where lambda is given in Armstrong, that is 10 to the power minus 8 centimeter, and V is the accelerating voltage in volts. So we see if the wavelength of a 150 volt electron is 1 Armstrong and 1.5 volt electron is 10 Armstrong. So we can write the Schrodinger equation in case of one free electron in a box like this: minus h cut square by 2 m grad square plus Vr psi is equals to E psi, is in effect of a generalization of the de Broglie relation to situations in which the potential energy Vr of the electron is a function of the position r. So in this equation, grad square equals to del 2 del x2, that is the Laplacian, plus del 2 del y2 plus del 2 del z2, and h cut is the h by 2 pi is the total energy, which is constant. So the function psi, right, is the wave function or eigenfunction, and has the significance that the when the properly normalized means psi star psi dx dy dz is the probability of finding the electron in the volume element dx dy dz, where psi star denotes the complex conjugate of the function psi. So we can see a connection to the Schrodinger equation with the de Broglie relation by considering the electron in free space with Vr, that is there is no potential, equals to 0. The wave function becomes grad square psi is equals to minus k square, no, sorry, minus h cut square twice m grad square psi is equals to E psi. So we may obtain a solution of this equation with E constant on taking as plane wave type, that is psi e to the power I k dot r. So we can see grad square psi is equals to minus k square psi, as this plane wave is the solution of the Schrodinger equation this equation must satisfy this Schrodinger equation. So which naturally turns out grad square psi equals to minus k square psi. And so psi is a solution when k and e are related by h cut square k square by twice m. Now k, called the wave vector, has the significance for free electrons that k is the modulus of k vector is nothing but 2 pi by lambda. And lambda is the wavelength, and on substitution we have E is equals to h cut square by twice m 2 pi by lambda whole thing square. As we put this value of the Broglie wavelength, we naturally get the value of E as p square by twice m, which is half mv square, which is exactly the classical energy for a free particle of mass m. We see that for a free particle, that the wave equation leads to the same connection between the energy and wavelength as does for the Broglie relation. So in the approximation that the conduction electrons are entirely free, we take their wave functions to have the form psi nearly equals to e to the power I k dot r. We must normalize it so that the integral of the probability density, that is psi star psi, over the allowed region of space is unity. That is the integration of psi star psi over all space dr equals to 1. And we accomplish this by setting psi is equals to 1 upon v to the power half e to the power I k dot r, where v is the volume, right, of the solid within which the electron is confined. So this is the difference between, as we consider in case of kinetic theory of gases, where the molecules are completely free and can take the velocities from 0 to infinity. But in this case, as electrons are not completely free, they are confined in solids, and there is ion cores. So electron can wander freely in the electron gas, but they cannot go out of the solid. That's why there is a restriction of the boundary condition which we have to impose in the Schrodinger equation. Unlike from the case of the molecules in ideal gas, although this is regarded as the same of the free electrons of solids, free electron gases in solids. So here V is the volume of the solid within which the electron is confined. So we also want the wave function to satisfy reasonable boundary conditions on the surface of the solids, right? For example, we can require the wave function to go to 0 on the surfaces. So the boundary conditions introduce a type of quantization into the problem. Consider an electron confined to a line of length L as shown in these figures. If we require that psi at 0, the initial point is 0, so as psi as L, and then the solutions of the wave equation in one dimension must be of the form psi n is equals to 2 by L to the power half sine n pi x by L. And we obtain the energy by substituting this psi n to the Schrodinger equation, which turns out to be energy quantization relations. En is equals to h cut square by twice m pi by L whole thing square n square, where n takes the values of the integer like 1, 2, 3. So the allowed energy levels are quantized in this way. Other values of energy being excluded as the corresponding psi's do not satisfy the boundary conditions, which are psi equals to 0 at here, or psi is equals to L here, are 0. So this figure is the first three wave functions for electron constrained to move in a line of length L. That's why we're solving the quantum mechanical behavior of the free particles in a box, right? So this is the first quantization relation we encountered in quantum mechanics, which is very different from the classical mechanics. In classical mechanics, we have E is equals to P square by M, where P is equals to mv. V takes the value from 0 to infinity. Their energies are continuous. Your energy can take any values, right? But in case of energy discretization of the energy level, there are only certain values of energy which are allowed, where n is the integer. So En are the integral multiple of pi square h cut square divided by twice nl square. And as we go on to the n largest values of n, the energy states are getting very closely spaced, and after all, at n equals to infinity, it is called the continuum state, right? So it is often convenient, particularly in 3 dimensions, to introduce the boundary conditions in different ways, right? The method is of periodic boundary conditions and in connection with the lattice vibrations. So we quantize the electrons in a cube of length L rather than uh, one-dimensional size L only, and we require the wave functions to be periodic in x, y, z with period L. So we require, for example, that psi x plus L y z is same as psi x y z with similar relations with the y and z coordinates. So free particles wave functions satisfying the periodicity requirement will be of the form psi n is equals to 1 by L to the power 3 by 2 e to the power I 2 pi by L nxx plus nyy plus nzz, where nx can take the value of 0 plus minus 1 plus minus 2, likewise ny and nz. So it is easy to see that this function is satisfactory for psi n x plus L y z is equals to, if we substitute x plus L here, so this turns out to be nx times x plus L, which is similar like psi n x y z, which is the our requirement or the condition of satisfying the wave functions to be periodic in x, y, and z. So here n, right, denotes the triplet of integers, which is the combination of nx, ny, and nz, and the energy corresponding to the solution is easily seen to be En is equals to h cut square by twice m 2 pi by L whole thing square nx square plus ny square plus nz square. That is h cut square n square divided by 2m v to the power 2/3. Here the volume V is equals to L cube, and the integer n square is equals to nothing but the summation of the nx square, ny square, and nz square. Here we note that the allowed values of the wave vector are given by nothing but k is equals to 2 pi by L into n. And we see that two types of boundary conditions are associated with two different types of wave functions. The previous one, where we considered the one-dimensional case, right, where psi equals to 0 at the boundaries, are of the form of standing waves. So these are the standing waves and have the property that the probability density psi star psi is equals to nothing but 2 by L times sine square n pi x by L, is a periodic function of x. However, the solution in latter case for periodic boundary conditions are of the form of traveling waves rather than standing waves, and give a uniform probability density as psi star psi is equals to 1 upon v. So these differences are not significant in free electron problem, but it turns out that when the interaction with the crystal lattice is taken into account, the traveling wave solutions have more direct physical importance than the standing wave solutions. So we shall work with the traveling waves. So as we have discussed, the ground state properties of the electron gas, we must follow that the Sommerfeld theory of metals and which is after the discovery of the Pauli exclusion principle, was needed to account for the bound electron states of atoms. Sommerfeld applied the same principle to the free electron gas of metals and thereby resolved the most flagrant thermal anomaly of the early Drude model. So in this application, Sommerfeld's model is nothing more than Drude's classical electron gas with the single modification that the electronic velocity distribution is taken to be the quantum Fermi-Dirac distribution rather than the classical Maxwell-Boltzmann distribution. So to justify both the use of the Fermi-Dirac distribution and its bold grafting onto the otherwise classical theory, we must examine the quantum theory of the electron gas. Kindly note that the electron gas, by the term electron gas, is to mean a gas of free and independent electrons, unless we are explicitly considering correlations due to electron-electron or electron-ion interactions, right? So for simplicity, we shall examine the ground state, that is T equals to 0, of the electron gas before studying it at non-zero temperatures. As it turns out, the properties of the ground state are of considerable interest in themselves. We shall find the room temperature for the electron gas at metallic densities is a very low temperature indeed, for many purposes indistinguishable from T equals to 0. Thus, many of the electronic properties of a metal hardly differ from their values at T equals to 0, even at room temperature. So quickly some calculations regarding the ground state properties of the electron gas. A single electron can be described by a wave function psi r and the specification of which of two possible orientations its spin possesses. If the electron gas has no interactions, the one electron wave function associated with a level of energy epsilon satisfies the time-independent Schrodinger equation minus h cat square by twice m del 2 del x2 plus del 2 del y2 plus del 2 del z2 psi r is equals to minus h cat square by twice m grad square psi r, that is epsilon psi r. Here we also make the free electron approximation so that no potential energy term appears in the Schrodinger equation. So we shall represent the confinement of the electron by the attraction of the ions to the volume V by a boundary condition on Schrodinger equation. So the choice of boundary condition, whenever one is dealing with problems that are not explicitly concerned with effects of the metallic surface, is to considerable degree at one's disposal and can be determined by mathematical convenience. For if the metal is sufficiently large, we should expect its bulk properties to be unaffected by the detailed configuration of its surface. So in this spirit, we first select the shape of the metal to suit our analytic convenience, and the time-honored choice is a cube of length L, which is p to the power 1/3, or it is L cube is equals to p, that is the cube. So we must append a boundary condition to the Schrodinger equation, reflecting that the fact that the electron is confined to this cube. We also make this choice in the belief that it will not affect calculated bulk properties. One possibility is to require the wave function psi r to vanish whenever r is on the surface of the cube. So this, however, is often unsatisfactory, for it leads to standing wave solutions of the Schrodinger equation, while the transport of charge and energy by the electrons is far more conveniently discussed in terms of running waves. A more satisfactory choice is to emphasize the inconsequences of the surface by disposing of it altogether. So we can do this by imagining each face of the cube to be joined to the phase opposite it, so that an electron coming on the surface is not reflected back in, but leaves the metal, simultaneously re-entering at a corresponding point on the opposite surface. Thus, if our metal were one-dimensional, we would simply replace the line from 0 to L to which the electrons were confined by a circle of circumference L. In 3 dimensions, the geometric embodiment of the boundary condition in which the three pairs of opposite faces on the cube are joined becomes topologically impossible to construct in 3 dimensional space. Nevertheless, the analytical form of the boundary condition is easily generalized. In 1 dimension, the circular model of a metal results in a boundary condition psi x plus L is equals to, sorry, in 1 dimension, a circular model of metal results in the boundary condition of psi x plus L is equals to psi x, and the generalization to a 3 dimensional cube is evidently psi x y z plus L is equals to psi x y z, and same for y plus L and x plus L. This equation is known as the Born-von Karman periodic boundary condition. We call it PBC, Born-von Karman PBC. So we shall encounter it often, sometimes in a more generalized form. So we now solve the Schrodinger equation subject to the boundary condition of Born-von Karman. So one can verify by differentiation that a solution neglecting the boundary condition is psi k r is equals to 1 upon root b to the power I k dot r with energy epsilon k is equals to h cut square by twice m, where k is any position independent vector. We have picked the normalization constant here 1 upon root b, so that the probability of finding the electron somewhere in the whole volume V is unity. That is 1 equals to integration over all space dr psi r mod square. So to see the significance of the vector k, that is the wave vector, note that the level psi k r is an eigenstate of the momentum operator p, that is p is equals to h cut by I del r. We all know that is h cut by I grad in 1 dimensional, which is px equals to h cut by I del x, and so on and so forth. With the eigenvalue p equals to h cut k as h cut by I, as sorry here as h cut by I del r is operating on e to the power I k dot r, h cut k e to the power I k dot r. So since a particle in an eigenstate of an operator has a definite value of the corresponding observable given by the eigenvalue, an electron in the level psi kr has definite momentum proportional to k, which is p equals to h cut k, and a velocity v is p by m of v is equals to h cut k by m. So in view of this, the energy can be written in the familiar classical form, epsilon is equals to p square by twice m, which is half mv square. We can also interpret k wave vector, the plane wave e to the power I k dot r is constant in a plane perpendicular to k, since such planes are defined by the equation k dot r equals to constant, right? K dot r equals to constant, and it is periodic along lines parallel to k with wavelength lambda equals to 2 pi by k, which is known to be the Dobroi wavelength. So we now invoke the boundary condition Born-von Karman. This permits only certain discrete values of k, since our boundary condition will be satisfied by the general wave equation only if e to the power I kxl, e to the power I kyl, and e to the power I kzl equals to 1. Since e to the power z equals to 1 only if z equals to 2 pi I n, where n is an integer, the components of the wave vector k must be of the form kx equals to 2 pi by L times nx, same likewise manner for ky and kz. So thus in a three-dimensional space with Cartesian axis kx, ky and kz, known as the k space, the allowed wave vectors are those whose coordinates along the three axes are given by integral multiples of 2 pi, which is illustrated in 2 dimensions in this figure. Generally, the only practical use one makes of the quantization condition in this, a kx equals to 2 pi nx, uh, kx equals to 2 pi nx by L. This is one kind of quantization uh, condition. One often needs to know that how many allowed values of k are contained in a region of k space that is enormous of the scale of 2 pi by L, and that therefore contains a vast number of allowed points. If the region is very large, then to an excellent approximation, the number of allowed points is just the volume of k space contained within the region divided by the volume of k space per point in the network of allowed values of k. So the latter volume, as shown in the figure, is just 2 pi by L whole thing cube. So we conclude that a region of k space of volume omega will contain omega by 2 pi by L whole thing cube, that is omega v by 8 pi cube, where we consider L cube is equals to v. So these many allowed values of k, or equivalently that the number of allowed k values per unit volume of k space, also known as the k space density of levels, right? K space density of levels is just v by 8 pi cube. Allowed values of k is just v by 8 pi cube. In practice, we shall deal with the k space region so large as 10 to the power 22 points and so regular that all intents and purposes of this equation and that equation can be regarded as exact. So we can begin to apply these important counting formulas shortly. And here, because we assume the electrons are non-interacting, we can build up n electron ground state by placing electrons into the allowed 1 electron levels we have just found. The Pauli exclusion principle plays a vital role in this construction. We may place at most 1 electron in each single electron level. So, right? So, because we assume that the electrons are non-interacting and we can build up n electron ground state by placing the electrons into the allowed 1 electron levels. So the Pauli exclusion principle is we may replace at most 1 electron in each single electron level, right? At most 1 electron. So 1 electron levels are specified by the wave vector scale and by the projection of the electron spin along the arbitrary axis, which can take either of the two values, either h cut by 2 or minus h cut by 2. Therefore, associated with each allowed wave vector k are two electronic states or electronic levels, one for each direction of the electron spin. Thus, in building up the n electron ground state, we begin by placing two electrons in the one electron level k equals to 0, which is the lowest possible one electron energy, that is epsilon equals to 0. So we then continue to add electrons, successively filling the one electron levels of lowest energy that are not already occupied. Since the energy of a one electron level is directly proportional to the square of its wave vector, then n, capital N, is enormous. The occupied region will be indistinguishable from a sphere. So the radius of this sphere is called Kf, F for Fermi, right? And this volume omega is 4/3 pi Kf cube. So according to this relation, this relation, the number of allowed values of K within the sphere is 4/3 pi Kf cube times V by 8 pi cube, which is Kf cube by 6 pi square V. Since each allowed K values leads to 2 electron levels for each spin value, in order to accommodate n electrons, we must have n equals to 2 Kf cube by 6 pi square times V. That is Kf cube by 3 pi square V. So thus, if we have n electrons in a volume V, that is the electronic density n equals to capital N by V, then the ground state of the n electron system is formed by occupying all single particle levels with k less than k, right? K less than k. What we say? If we have n electrons in volume V, that is the electronic density small n is equals to n upon V, then the ground state of the n electron system is formed by occupying all single particle levels with k less than kf and leaving all those with k greater than kf unoccupied, where kf is given by the condition small n is equals to this kf cube divided by 3 pi square. Below kf, all are above kf, there is a kind of demarcation at kf, that is the Fermi wave vector. So within this condition, our electronic density n becomes kf cube divided by 3 pi square, or simply kf equals to 3 pi square n to the power 1/3. This is a very important relation regarding the Fermi wave vector and the electronic density of free electron gas. Kf is equals to 3 pi square n to the power 1/3. So this free and independent electron ground state is described by some rather unimaginative nomenclature. The sphere of radius k, if we construct a sphere of radius kf, the Fermi wave vector, which is the Fermi wave vector, right, containing the occupied one electron levels is called the Fermi sphere. So the sphere of radius k, the Fermi wave vector containing the occupied one electron levels is called the Fermi sphere. The surface of the Fermi sphere, which separates the occupied from the unoccupied levels, is called the Fermi surface, right? The surface of the Fermi sphere, which separates the occupied from the unoccupied levels, is called the Fermi surface. And the momentum h cut kf is equals to pf of the occupied one electron levels of highest energy is known as the Fermi momentum. And their energy epsilon f is equals to h cut square kf square divided by twice m is the Fermi energy. So these are Fermi momentum, these are Fermi energy. And their velocity Vf is equals to Pf by m is the Fermi velocity. Fermi velocity. The Fermi velocity plays a role in the theory of metals comparable to the thermal velocity V, which is 3 kBT by m to the power half in a classical gas, starting from the Maxwell-Boltzmann statistics. So in these quantities, one can evaluate in terms of conduction electron density. For estimating them numerically, it is often more convenient to express them in terms of the dimensionless parameter. Already we have discussed Rs by the Moore magneton, uh, which varies from about 2 to 6 in the metallic elements. Then Kf is equals to 9 pi by 4 to the power 1/3 divided by Rs, that is 1.92 divided by Rs, or Kf is equal to 3.63 divided by Rs by A0 Armstrong inverse. So since the Fermi wave vector is of the order of inverse Armstrongs, the de Broglie wavelength of the most energetic electrons is of the order of Armstrong, and the Fermi velocity Vf is equals to h cut by m Kf, that is 4.2 divided by Rs by A naught into 10 to the power 8 centimeter per second. So this is a substantial velocity, about 1% of the velocity of light. 1% of velocity of light, that is c. From the viewpoint of classical statistical mechanics, this is quite a surprising result, for we are describing the ground state, that is t equals to 0, and all particles in a classical gas have zero velocity at t equals to 0. So even at room temperature, the thermal or the average velocity for a classical particle with the electronic mass is only of order 10 to the power 7 centimeter per second. So the Fermi energy is conveniently written in the form, since A0 is h cut square divided by m e square, right? H cut square by m e square. Uh, my epsilon f h cut square kf square divided by twice m, that is e square by twice a0 kf a0 square. Here e square by a0 2a0 is known as Rydberg, that is Ry, is the ground state binding energy of the hydrogen atom, that is 13.6 electron volt, and the Rydberg is as convenient a unit of atomic energies in the Bohr radius is of atomic distances. So here kf a0 is of the order of unity. So this equation of the Fermi energy demonstrates that the Fermi energy has the magnitude of a typical atomic binding energy. So using the relation Kf is equals to 3.63 divided by Rs by A0, right? And A0 is simply first Bohr magneton is 0.53 Armstrong. We find the explicit numerical form epsilon F is equals to 50.1 electron volt divided by Rs by A0 whole thing square, indicating a range of Fermi energies for the densities of metallic elements between 1.5 to 15 electron volts. So these are all from the ground state properties of the electron gas.